All righty. So we're going to do now section 9. The title's a little bit misleading in the sense that we are going to talk about the general definition of statistical information, but then we're going to use it to do very, very cool stuff and learn why the sampling distribution of many parameters are normally distributed. Very cool things in this lecture, I think. Lots of different pieces, but hopefully also some familiar looking things as well. So let's start. I'm going to start with the standard setup. I have my data, my model. Things are independent and identically distributed. I'm interested in learning about theta, usual stuff. My likelihood function is the product of the F's. And of course, I can do everything on the log scale. And in fact, most of what I'm going to do is operate on the log scale. And we learned from the last time, we learned what the score function is. So the score function for one observation is the derivative of the log likelihood. That's the derivative of the log likelihood with respect to theta, which we write like this. And of course, the derivative of the log of something is 1 over, and then I got to follow the chain rule for the other piece. And we showed that when in fact the model that the score function is based on is equal to the model that the expectation takes, right? So when the working model is equal to the true model, then what happens is, on average, that score function is 0. So good things happen. And we'll see why that's good. And then we learned something new. We learned something called Fisher's information, which looked kind of like a little bit of a weird thing. We're going to connect it to something that's much more intuitive in just a second. But this I for information is Fisher's expected information, which was by definition, the variance of the score function is the Fisher's expected information, which we could also write as just the expected value of the score function squared, because remember, the variance of x is equal to the expected value of x squared minus the expected value of x squared. But for us, the score function has average 0. And by x here, I mean s, s, s. All right, so that's where we left off. Let's take a look at where we're going now. I'm going to start with something called Bartlett's second identity. And actually, there are a whole bunch of Bartlett identities. The second is one of them and is one that has a very large impact, but they're moment identities. And so these are Bartlett's second identity says, hey, you know the variance of that score function? You know that thing that was complicated to compute? It was the expected value of the square of the score function. Yeah, that's kind of yucky. And so Bartlett said, hey, man, I'm not going to compute this all the time. I want a shortcut. And so what he was able to show is that under certain conditions, which we'll talk about in a second, like when the working model and the true model are the same, then the expected value of the square of the score function is equal to the negative of the second derivative of the log likelihood. Now, wait a second. These things are kind of related, right? So the variance of the score function here, okay, is equal to the expected value of the score function squared is equal to minus the derivative of the score function. And I'm going to use special notation because I can't keep typing actually partial theta here. So I'm going to use this S prime business here as the expected value. So basically the second derivative is very closely related to the square of the first derivative. And on average, they're the same thing. Well, once you negate one side. And so this is going to be nice because it's going to turn out to be much easier to compute this guy rather than the original piece. You got to keep in mind though, that this part here in black, this is the shortcut. And that this part here, this is the official definition of the variance of the score function. So sometimes the shortcut, and this is what we're going to work up to this over the next set of lectures. Sometimes the shortcut is not equal to the official version. And in that case, we're going to have a problem, and we're going to have to figure out what to do. But that's for another time. For now, all we know is that there is a shortcut for computing this particular information piece. All right, notice the notation here. The derivative of the score function is just this s prime. So I'm using primes instead of derivatives. So the derivative of the density is f prime. Just makes life easier. All right, there's a proof. I'm not going to spend too much time on this, but I am going to go through it only because it just involves really the chain rule, and we're done. And so I think it's helpful to see. So we'll start with the fact that the density integrates to 1. No problem. And over here, I'm writing this in shorthand, right? So these are the same results. This is the full notation, and this is the shorthand. And the proof here is going to be in terms of shorthand because it's just easier to write. So if, in fact, I take the derivative just of both sides, just like I did before, I take the derivative here and the derivative here, I get this piece here, which is that the derivative of this thing is equal to 0. And then, of course, I can take the derivative again, and the derivative of 0 is still 0. So I get these sets of equations, which are going to be super helpful. The other thing that's going to be useful is this is the score function. If you remember, the score function SI was partial theta of log of fx theta, right? It's the derivative score function s. Wow, that's pretty terrible handwriting there. Let's see if we can't clean that up a bit. This is, whoops, going backwards. There we go. Now, if I pull the derivative through, the derivative of log of f is 1 over f of x theta. And then I have times partial theta of f x theta. So this is just f prime over f. So that is that piece right there. We've done that now several times. Now, if I want to take the derivative again of this thing, I'm basically going to use this formula, and I'm going to use the chain rule. But when you have division, you've got the chain rule, right? The chain rule, which is the top times the derivative of the bottom minus the bottom times the derivative of the top over all the bottom squared. So let's how do we do that? Well, I'm taking the derivative of this fraction, taking the derivative of that fraction. So it's all over the bottom squared here. And so it's the bottom minus the derivative of the top. F prime, take another derivative is another prime. And then it's times the top times the derivative of the bottom. So it's f prime, f prime. So no problem. It turns out now I can cancel a few quantities. So I can break this up into this piece plus this piece. And this is going to be helpful for the next part. Remember, the integral of, we're going to use this piece here. So let's go over here. I'm going to write it down just first. Remember that the integral of f is equal to 1. And then we saw that the integral of the derivative was 0. And then we saw that the integral, what is that there? And then we saw that the integral of the second derivative was also 0. Those are things that we just did from the last page that are going to be useful. Now, we proved a couple of classes ago that the expected value of the score function was 0. This is how this looks in the shorthand notation. Here's the derivative. This is the score function. This f of x, this outer part, is the actual expectation taking, right? And we proved that this thing was 0. So these f's cancel here. Let's see, hold on. Let's undo those things. So this is just this is by the definition. These s cancel, and I get this thing, and we had already proved that that thing was 0. And we knew that from the beginning, so there's several different ways that we can get there. All right, well, now I'm interested in the next piece, which is the derivative of that thing, which is partial theta of SI. Well, we calculated that on the last page over here. So what I'm going to do is I'm going to take the expected value of this thing and write it just down here. So the expected value of that thing is in here's the first term, and here was the second term. So this is term 1, and this is term 2. I'm just going back. Remember here, this is term 1, and this is term 2. I'm going to take the expected value of this and the expected value of that. Here they are, right here, and right here. Okay. And then some canceling is about to happen. So let's cancel up some stuff. So let's use a good color for canceling. How about this little pinky color here? These are going to cancel. So I get just this thing, which I know from here is 0. So that's that 0. And then this thing actually, interestingly, is just the score function squared. So I'm going to leave that alone. But this is an integral. And this is, in fact, the expected value of the score function squared. And that's this thing. Well, now it's all done. It's actually pretty simple. I have this equals this. Whoops. Which is literally this result. And written out in big old fat messy notation, I have the expected value of s squared is equal to minus here. This is the second derivative, partial squared log f of x I. Oh my God. All right. All right, hold on. Let's just try. It's right down. Ooh, it's right down here. Is this thing are the same things. And this, of course, this piece here is, of course, the information. So we have a shortcut now for calculating the information. And so this, the way I think about this, I'm just going to write down one more time. This is the shortcut. Okay. And this is the, definition. And they're equal if and only if the, if and only if the working model is equal to the true model. Why do I need that? Well, if you look up here, this only happens when the working and true model are the same, because I had to take expected values under the correct model. All right. We're going to come back to that. I'm going to say that about 80 million times as we go through here, but I think it's important. Now, this piece here, this guy here, this is a constant. This is information. When this was the Poisson distribution, it was 1 over lambda. For the normal distribution, 1 over sigma squared. For the binomial distribution, it's 1 over p times 1 minus p. It's a constant. Well, I can estimate it essentially by calculating this thing. Well, what do you mean? Well, this is just some function. It's just some function of the data. So this is an average. This is the average second derivative of the log likelihood. And so what do we know by the law of large numbers? Well, the law of large numbers turns sample averages into population averages. Boom. And then this is the expected value of this thing, which is negative of the information. So you just have to pay attention to a sign. I can put the negative over here and make this a positive if I want. So I can move that from side to side. The important thing is when I calculate this score function, this second derivative, I have to calculate it at a particular value. Just like when we calculated the score function, we needed to, when we calculated the score function at theta hat, right? When we calculated the score function log f of x partial theta. This was the score function. When we calculated the score function at theta hat, that equals 0. And that's by definition because theta hat is the value that makes the score function 0. So it's the same thing when I calculate the second derivative. I'm going to plug in here I'm going to plug in the maximum likelihood estimator. And we know that the maximum likelihood estimator will converge to the true value. So that convergence goes on here too. So there's actually two convergences. So if you're careful, you can see I got two convergences. One is this convergence here of the sum to the other. The other is this convergence here to the true value right here. They go on together at the same time. All right. Let's do an example. An example is great to help fix ideas and understand what's going on. I'm going to go back to my Poisson example. Here's the Poisson density, and here it is taking the logs. And so the score function, which we saw before, which was the derivative, the score function is the derivative of the log likelihood, right? The score function is the first derivative of the log likelihood. First derivative of the log likelihood, we computed that, and that was that thing. Now I want the second derivative with respect to lambda. So I want the derivative of the score function, which is the second derivative of the log likelihood. Because remember, the score function is already the first. And so that is just this thing. Because partial lambda of xi over lambda minus 1. So what is the derivative of lambda squared? You get a minus 1, and then your xi stays up here. And so that's exactly what's here. There you go. Well, let's calculate this thing. Let's try out our inequality here. So let's calculate this thing. Let's take the expected value of this thing. So I'm going to plug that guy in there. So this is not too hard. It's the expected value, this by definition. And all I do is I plug this in here. Notice here, I've already taken care of the minus sign by putting it out front. So that gets rid of that minus sign. The expected value of the xi is, this is lambda if the true model equals the working model, right? Which we are assuming yes for the moment. So then I get 1 over lambda, which is the information, which is it should be. And in fact, if I add in the sum here, I just get an n. And this is the information in the observation of n observations. Now, this is the expected value. This is what happens in the limit. What happens in a particular sample? Well, in a particular sample, I'm not taking the expected value. So I would just actually calculate this thing, which is an average right here. Whoops. I don't want to write over that. So this thing right here, which is an average. So I have the minus sign out front. I have the minus sign out front to just keep the minus out front here. And then this is, in some sense, this is the average second derivative of the log likelihood, right? Average second derivative of the log likelihood. So, and this thing is, you can write like this. This is just notation change. Notation change right here. And now I'm just plugging in. I'm plugging in this part here. Let's see if I can write here. So I'm plugging in this part here without the minus sign. And that's going right there. Bing. The ends cancel and I get this thing. X bar over lambda squared, which will converge to 1 over our lambda. But if and only if lambda, whoops, too ahead of myself. If and only if X bar converges to lambda. So dastardly looking lambda there. Okay, so there we go. And this only happens if under some conditions, like if the model is true model. So this is what it says here. This only happens when X bar converges to lambda. That is, only if the Poisson model assumption is correct. So when the working model fails, the average second derivative may not be a consistent estimate of the information. That is, this thing, your estimate of the information may not go to what the true information is in general. Now, we're going to be able to correct this behavior eventually when we come back and discuss robustness. But for now, you can see why this is important to keep track of. All right, now is a good time to just take a quick pause. Let me take a drink. And in fact, I'm just going to take a pause here for the actual thing and come back, and we'll start the next half in a second.